70% yield. So we obtain these gold scorpionate complexes, okay, that we are going to use. And here we have an example for the gold scorpionates and their heterogenization on these functionalized nanotubes. We did on these functionalized nanotubes, also on the oxidized nanotubes and on the normal nanotubes, and all on the other carbon materials as well, functionalized or not. So a lot of samples were tested. So this functionalization, just as an example, it was to have 2% metal in weight, and it was dissolved in methanol at room temperature, and it was a very fast process. From 2 to 8 hours, it could be totally dissolved. Of course, other complexes of other metals, like, for example, iron, copper, and vanadium, or other ligands, might need more time or other solvents, but like ethanol, here we could do it in methanol. So we have here the gold complex connected, bound to the carbon nanotubes. Of course, it's not just one gold complex. This is just for you to see. There are all over more gold complexes anchored on the carbon material. They are spread all over. And you see, it's a very fast process because we do ultraviolet visible spectrometry just to check. And here it's the solution before anchorage, okay? So we have very large bands above what would be measurable. But after 1 hour with the carbon complex, it's anchored on the surface. So if we do a ultraviolet visible of the supernatant of the liquid, we see there is almost nothing there. After 1 hour and 2 hours, there is almost nothing. So the gold complex was totally anchored on the support. And this was the first report of heterogenization of gold complexes on carbon supports. Before, there was only heterogenization on the oxides and other materials, but on carbon supports, this work of ours was the first one. And those catalysts were tested for the oxidation of cyclohexane. So cyclohexane to give cyclohexanol and cyclohexanone. So the carbon, the alcohol, and the acetone. So this reaction is very important because these two materials are important reagents for the production of adipic acid and caprolactam that are used in the manufacture of nylon polymers. So for ladies' pantyhose, for these fibers, for many other uses. And the present industrial process to produce nylon, to produce, not to produce nylon, but to produce cyclohexanol and cyclohexanone that are going to be used in the manufacture of nylon. So the industrial process for this reaction uses a homogeneous cobalt catalyst, oxygen, 150 degrees, and it only has 80 to 85% selectivity, and the yields are very low, from 4 to 12%, the current industrial process. So if we can improve this, it's very good. And we could, using here hydrogen peroxide and very much lower at room temperature, and as we are going to see, only 6 hours reaction, so it was better. So we have here the oxidation of cyclohexane, okay? The best results were obtained with the anchorage of this complex. So those are the ones that I'm showing here. And here we have the homogeneous complex, so not anchored. So we have here this ton. So, okay, the ton is moles of product per moles of gold. And we see that if we heterogenize the complex, we have much higher values, okay? So heterogenization produces much better results than the homogeneous one. And we see that carbon nanotubes here produce the best results, and also this treatment with nitric oxide and with sodium hydroxide. So these ones, the OXNA,
Hello,
has
madam.
better results, not only here on carbon nanotubes,
Hello,
but all on activated carbon
madam.
and
The message is there on
carbon
the
sharing.
screen, right? Make a okay.
I'm sorry,
Hello.
someone said
Okay.
something?
Okay. One
Okay,
message is there on
okay.
the on your screen. Make it okay. Say okay now. Yeah.
I don't have any message on my
Okay,
screen.
then it's continue. Okay, then. Okay, okay. Okay, yeah.
No message appeared. I'm
Okay.
sorry.
Okay, madam. Continue. Yeah.
Okay, thank you. So we
Okay.
see here that these were the best results, and in all cases, high selectivities were obtained. So no trace of byproducts were found, only cyclohexanol and cyclohexanol. And there was no need for acids because sometimes we need to use a little bit of acid to acidify the aminium and for the reaction to be better, but it was no need. In this case, it's even an inhibitor in these systems. And also, only a small amount of oxidant was needed. So here, only 10 millimoles of hydrogen peroxide. And the results of the gold scorpionates anchored on carbon materials were much better than those obtained with gold nanoparticles on the carbon supports and gold nanoparticles on oxide supports. So that was interesting. The best result obtained was a yield of 16%, which is higher than the industrial process. And remember, the industrial process needed 150 degrees, and we could do it at room temperature and only in 6 hours. So it's quite good. And we could also obtain a good catalyst recyclability, because you see here that a few cycles, of course, there is a small loss of activity that's due to a small leaching, but we can recycle it. If we used homogeneously only the support, we could not recycle, we could not obtain it back. Also, we tested immobilization of scorpionate complexes of other metals. So here, iron, copper, and vanadium, for example. And we also could obtain good yields in 6 hours, but they needed acid. The ones on gold did not need. The best result was obtained with an iron 2 complex. So this one here, where is an R, it was with a CH, and here 2 chlorides. Okay, so the best yield was 21%. Compared to the industrial process, is much better, and it's also better than the 16% obtained with the scorpionates. But remember, the scorpionates did not need acid, and here we have to add a little bit of acid. And also no trace of byproducts and recyclability up to 5 cycles without much activity loss. So it was also good. We also use this complex heterogenized on carbon nanotubes for the oxidation of alcohols to ketones, which is another process of industrial importance, but this time using microwave irradiation, okay? And here we used at 80 degrees and with aqueous terbutyl hydroperoxide. No solvent was needed because the solvent was the alcohol itself, and with or without this radical, okay, the tempo, so-called tempo radical, okay? And the use of microwave usually allows to obtain similar yields in shorter times and lower temperatures. So it was tested for this reaction, the oxidation of cyclohexanol to produce cyclohexanone, okay? And also for the oxidation of phenylethanol to produce acetophenone. That is a precursor, very useful for useful resins, fragrances, and raw material for pharmaceutical synthesis. And this was the first report of a carbon scorpionate complex being used for alcohol oxidation, both in homogeneous and heterogeneous conditions. So we used it. And here we have the results for cyclohexanol oxidation to produce cyclohexanone. And you see here, this is the iron complex. So this complex here alone has these yields. So we are seeing it here with time. Okay, so 1 hour was the best yield. So we have here only the complex. If we add the radical tempo, it increases. If it's heterogenized, it's even better. And of course, the best result is heterogenized, and with the tempo radical, we obtain a yield of 98%. Okay, so this was for cyclohexanol. We also tested for 1 phenylethanol, okay, and the same trend, and the best result was 94%, okay, for this complex. So we see heterogenization is also much better. We also obtain nice selectivities, no trace of byproducts, and better results with the tempo radical. And if we do a recycling, we could do it up to 12. We did it up to 12 cycles, and there is a small loss of activity, again, due to leaching. It's difficult to not to happen. And the use of microwave allows to obtain these very high yields in 1 hour, because without microwave, only in an oil bath eating, only 22% were obtained after 24 hours. So you see here, in 1 hour, we obtain above 90% yield using microwave. So that is the advantage. We also tested the oxidation of alkanes and alcohols using microwave, and this same iron scorpionate complex heterogenized on different carbon supports. And this was a cover of this number of ChemCatChem journal. And we have here the carbon materials that were used to heterogenize this complex. It was graphene oxide, single-walled carbon nanohorns, graphene nanoplatelets, reduced graphene oxide, and nanodiamonds. So a lot of carbon materials. Okay, the best results were obtained with this scorpionate, and for this reaction, cyclohexane to produce cyclohexanone and cyclohexanone, we have here the results, and it was interesting. Of course, if you compare here an oil bath in yellow with microwave, of course, very much higher yields, okay? But we see that heterogenization is only beneficial on this carbon support, on the single-walled carbon nanohorns oxidized. You see here, this is the complex, and alone, and not heterogenized. If we heterogenized on nanodiamonds, on graphene oxide, the yields are lower. But if we heterogenized on carbon nanohorns, oxidized, that's the only case in which it is better. And again, in all cases, high selectivity, no trace of byproducts. And if we see here the recycling, okay, we see that there is a decrease in activity, and here after 9 cycles is a total leaching. Too bad. We also tested not just for the oxidation of cyclohexane, but of 1-phenylethanol to produce acetophenone, and we could obtain 97% yield and a very good recycling, a little bit of activity loss, okay, and just 1 hour, okay, for the alcohol oxidation. We also tested the microwave oxidation catalyzed by vanadium scorpionate complexes on carbon nanotubes. This was also cover of this journal, Chemistry and Asian Journal. And we tested for the oxidation of orthometa and parachilanes to the corresponding methylbenzyl alcohols, to aldehydes and to oleic acids, okay? So we tested these two vanadium scorpionate complexes, and the best results were obtained with this complex, number 2 complex, on carbon nanotubes. And we see here the yields for orthochelane, meta, and parachylane. So it was better for parachylane. We obtained a yield of about 50%, okay, at 80 degrees. And again, the recycling was also good. Okay, the recycling, a little bit of activity loss after 6 cycles, but well, that's unavoidable. And we also tested the microwave-assisted oxidation using heterogenized commercial gold complexes. So these were the complexes that were used. They are commercial complexes. We did not need to synthesize them in the lab. So we just anchored them on the carbon materials. And this was also a cover of this special ChemCatChem issue. And it had also a cover profile with a small interview to the authors. And the results were also interesting. So the heterogenization results for cyclohexane oxidation, okay, see here we have homogeneous, and if we anchor on carbon support, see the best result is there, heterogenization is better. And again, carbon nanotubes, and this oxidizing treatment gives the better results, and the best results were obtained with this complex that is drawn there. And the best result was 26% yield. Of course, it's better than the 90%, the 60%, 16 with gold scorpionates. But here we had to use acids, and the scorpionates did not need acid. And also the scorpionates used milder oxidants, that was hydrogen peroxide, and we had to use TBHP, the terbutyl hydroperoxide. Also bad, but it was better than the iron scorpionates that had 21% and also used acid, but lower than the scorpionates on carbon nanohorns. Remember, had a 29% yield, but also used acid and TBHP. So we have to decide what we prefer. But okay, good recyclability was also obtained with similar level of activity, so not much here deactivation. And again, high selectivity, no trace of byproducts. Here we have the results, the best results for one phenol oxidation. So it was obtained with this complex, with phosphine, okay? This was for the alcohol oxidation. And we have here homogeneous, and of course, when we heterogenize, it's better, okay? And again, carbon nanotubes and this treatment are better results. The best yield was 96%, slightly higher than gold oxide supports, but slightly lower than on iron scorpionates, that was 98%. And again, recycling, we could recycle up to several cycles, okay? But there is a small activity loss, of course, due to leaching after some cycles, after the 8th cycle. We also tested this gold 3 commercial complex for this reaction, that is hydrocarboxylation of cyclohexane, okay, to produce cyclohexane carboxylic acid, okay? So this was the complex. And it was heterogenized on carbon materials. And again, we see the best result on carbon nanotubes oxides. So best results, of course, heterogenizing, and again, with good recyclability. So it also works for this reaction. And we also tested other vanadium complexes. So these Schiff-based ligands that were tested, that were synthesized this way. I'm not going to go into much details because not much time. So they were produced by reflux with this vanadium precursor. And here we obtain these complexes, these and these according to the different conditions used for synthesis. So we obtain this type of vanadium complexes. And the catalytic activity for one phenol oxidation, it was tested. So this is in homogeneous, the homogeneous catalyst, and the best result was obtained with this complex 5, okay, for yield of 94%, very good selectivity as expected. Complexes 2 and 4, that are these ones with OH and NH2, they could only be supported on nano diamonds. It was interesting. And the best result was obtained in nano diamonds, non-functionalized, because if we functionalize them, the result is worse, but of course is better than the homogeneous one. So best result was this complex with 91%, and again, very good selectivity. And here we have the other complexes that could be anchored on all carbon materials. Those two complexes only on nano diamonds. They were very, very selective. So we see here the best results with carbon nanotubes oxidized with sodium hydroxides as expected. Then we have the best results in general were obtained with carbon nanotubes, but here we have homogeneous, so only this one was better. And of course, nanotubes, the nanodiamonds were also good, and these ones were worse. Okay, so the best result was complex number 6 here with NH2, here it's this X, and it was 96% yield and very high selectivity as well. The recyclability, see here on nanodiamonds, well, there is a little bit of bleaching, but on carbon nanotubes is much better. Okay, so it seems that the phenolate and carboxylate treatments are very efficient as coordinating sites. They anchor the complexes better. And almost no vanadium was detected on leaching. See, very good up to 10 cycles. We also tested the microwave-assisted oxidation of cyclohexane using this oxido and deoxido vanadium complexes. And again, we saw that heterogenization produced better results than homogeneous, again, for this reaction. And the carbon nanotubes and the oxidation treatment gave better results. We have them here. So for complex 1 and complex 2, and the best result was 20% yield. Remember this reaction, the industrial process is only from 4 to 12%. So it was a process, well, okay, similar to the industrial one, but it was at lower temperatures than they use. Again, high selectivity and no need for acids. Okay, we used microwave and only a small amount of oxidant needed. So we see here on carbon nanotubes is better than on activated carbon. See here, but the activity decreases with time. So complex 2 was better. And again, the activity loss was due to leaching. Okay, some conclusions. All catalysts, heterogeneous and homogeneous, were very selective for alkane and alkyl reactions, so no trace of byproducts detected. The supported complexes showed higher catalytic activity than the homogeneous ones, also in general, of course. And it's possible that there is a stabilizing effect of the support. For example, it doesn't allow to make dimers or other species. And also in general, the complexes supported on oxidized and sodium hydroxide treated materials gave the best results. So it's possible that these more stable phenolates and carboxylate groups, they give better coordination sites, anchoration sites for the complexes. And also the best results were obtained for the carbon nanotube materials in general, and it might be a textural effect. For example, these materials are tubes, so they have no porosity on them, okay? So it might allow easier accessibility of the reactants to the active centers, or else an electronic effect because of the graphitic structure, okay, that might enhance reactions between reactants and intermediate radicals. We don't know, it's just some hypothesis. And the heterogeneized systems, they also showed good recyclability. They allow easier separation of catalysts and reaction mixtures. So minimize workout procedures, reduce costs, decrease the production of toxic waste. So I have all those advantages. So this research would not be possible without the collaboration of these entities for financing and etc. And I invite you to visit my country, which is very beautiful. So you have here some nice images. So thank you for the attention. And if you have questions, I'll be ready to answer. Thank you.
Thank you very much, Professor Sonia, for your wonderful talk. I believe the audience present here enjoyed a lot. Now, would you like to take one or two questions from audience? Any questions?
Yes. Dr. Sonia, is it audible?
Yes, I can hear you.
Yes, it was nice talk on the gold complexes, that is called as gold scorpionated complexes with the carbon nanotube and several diamond nanotubes. Okay. So my question is on the recyclability. You had saying that the gold, vanadium, and iron scorpionated, that is having the good recyclability, but at the diamond mediated, nano diamond material having the lower recyclability. What is the reason?
Yes, well, we also do not know the reason, here. We also do not know the reason here. Oh, here. We also do not know. We just found a very higher leaching. So because okay, the best result was obtained with nanodiamonds that were not functionalized. Okay, so it was easy for the complex to go away. But here, these results with the oxidized sample, okay, these phenolate and carboxylate groups, they could anchor the metal more easily. So it was easier to recycle. But with nanodiamonds, as it was tested, the recycling for the sample without this treatment, so it was easier to leach. We did not test of the with the oxidized nanodiamond sample, okay, because here the results were lower. See, so this the best results with nanodiamond. So we tested the recyclability. These ones, maybe it would anchor better, yes, but that it was lower activity, we did not test.
And the second more important thing, and moreover, I'd like to tell you, I'd like to ask this gold complex, and that is gold complex that is scorpionate with graphene based material. This is a bulky molecule. So whenever there is a conversion, yeah, oxidation of alcohol to the ketones. So is there a possibility there is a intermediate material formation? Yeah, there is a disturbance. Yeah, there is a we can say steric effect.
Yes, it's possible that there is also steric effects. Yes, that I did not completely understand your question, but you were saying if there is a possible steric effect. Yes,
because it is bulky molecule.
Yes, for example, here with vanadium, some complexes are bulkier than others. It's possible that there is a steric effect. Yes, many effects are possible, of course. Of course, if you read the papers, then we give some explanations. But here on 30 minutes, it was not possible to give all those explanations. But I wanted to give as much results as possible.
Okay, good. Nice talk.
Thank you.
Any other question? Professor Sonia, I have one curiosity. You are using metal complex with your carbon support, right? Metal complex are using with iron, copper, gold.
I'm sorry, I'm not hearing you well.
Hello. So the metal ions present like iron, copper.
Yes, iron and copper.
They are they are present in ferrous in plastic. So in this oxidation process,
Here for iron, yes, I studied iron and copper, and iron was the best result, but it needed acids. I'm not sure if that's what you are asking. I don't understand everything. I think the transmission was stopped or not. I don't know. I stopped hearing you.
so I think some communication problem here. Okay, thank you, Professor.
Okay, thank you.
Thank you, Professor Sonia. We really appreciate your work, particularly selectivity and yield of the catalyst. Thank you once again for your excellent talk, and we
Thank
hope
you.
in some future occasion you come here and physically present your lecture. Okay?
Sure.
Thank you very much.
Thank you. Thank you.
So next we move to our next talk. The speaker is Dr. Mohammad Abu bin Hassan Sushan. Welcome, sir. Dr. Mohammad Abu bin Hassan Sushan is a professor of chemistry and director of the Dhaka University Nanotechnology Center at Dhaka University, Bangladesh. He received his PhD degree from Yokohama National University, Japan in 2000 as the next scholar and was awarded BBL, JSPS, Crest and Beach Fellowship. He has about 225 articles, including 3 books and 30 book chapters. He collaborates with 14 renowned laboratories and visited 11 countries. He received prestigious awards from different national and international organizations. He served as the national representative of Division 1 of IUPAC and has been a fellow of Bangladesh Academy of Science and IUPAC. His citations are about 12, more than 12,000. Age index is 34 and item index is 101. So with this introduction, I invite Dr. Mohammad Abu bin Hassan Sushan to present his lecture.
Thank you for the nice introduction. Do you hear me?
Yes, sir.
Okay, thank you. So actually, I would like first to express my gratitude to the organizers, Professor Gurnolle. He is my very good friend, and Professor N.B. Singh. So actually, he is like my local guardian in India. I always have affections from him. But very unfortunately, as you know, that I was supposed to go to in person and present yesterday, but I could not get the passport back due possibly to many holidays in Bangladesh as well as national election in India. So I am really sorry that I made the inconvenience for you, but at least I am happy that I can share some time with you online. So as I have been introduced, you can see that I work for the Department of Chemistry, University of Dhaka, and I have a laboratory here. We established Material Chemistry Research Laboratory in the department, and recently I have been given the charge of the Director of the Nanotechnology Center. So today, actually, my lecture will focus on the development or say preparation of some nanostructured materials. In particular, you can see nanostructured zinc oxide, very common say band gap materials. So, but I will be using a different methodology. So methodology, hydrothermal method, that is not a very new one, but I am possibly going to use or report here the use of double salt ionic liquids, that soft template for preparation of nanostructured zinc oxide for the first time. So we know about zinc oxide nanoparticles. I am sure that there will be nobody here who does not know about this. So this is a semiconductor with a wide band gap, and it has a higher exciton binding energy and more resistant to radiation. And interestingly, they show antibacterial activity in nano level. These are well-known facts. But interesting thing is that zinc oxide nanoparticles can be prepared in many different morphologies. Not only say dimension, it can be spherical, capsule-like, rod-like, petal-shaped, flakes, flower, nanocluster, nanosheet, wide variation in the morphology, size and shape. So, is this variation really important? And why zinc oxide nanostructure with tunable morphology may be necessary? So, as I already mentioned, it has many different shapes. Some of the beautiful shapes are shown here: nanorod, nanopyramid, nanoneedle, woodside structure, cubic structure, nanosheets, nanocomb, and nanoflowers or snowflakes. So if we survey the literature, we can see that. So these specific shapes or morphologies find application in many different areas. For example, nanorods were reported to be used in gas sensor fabrication or antimicrobial activities. And nanopyramid, they showed antimicrobial or photocatalytic action. And we can see that nanoflowers were used for dye removal. And for photocatalytic activity, you could use nanocomb. sensor fabrication, we are finding applications from nano sheets, and for removal of heavy metals, cubic structures were very important. And as usual, hexagonal wood structure, they showed antimicrobial, photocatalytic, and dye removal activities. And nano needle, they showed electrical and antibacterial properties. So zinc oxide, so we can see that it has the dependent on morphology. The application is very versatile, very wide. So zinc oxide nanostructures with controllable morphology are highly desirable for task-specific applications. Since we can say tune the morphology, if we can tune the morphology, we can use very special or task-specific application of zinc oxide nanostructures. So now comes ionic liquid. So as I mentioned, I will be reporting the use of double salt ionic liquids. So before going to double salt ionic liquids, let me first introduce the ionic liquids and how ionic liquids are used to control the morphology. And then I will show how can the double salts be beneficial for the tuning the nanostructures. So we can see sodium chloride. So this is stable salt. This is very high melting temperature, we know. But ionic liquid, so these are comprise only ions, cation and anion combination like sodium chloride. This has also the combination of ions. But say symmetric anion and symmetric cation, this gives rise to say ionic solid like sodium chloride with very high melting temperature. But here you can see that the cation is asymmetric. So this asymmetric structure of the cation can yield some salts, ionic salts that are liquid at room temperature or even far below room temperature. Let us see the examples. For example, if we have the cation like this one, and anion, we have changed from bromide, say tetrafluoroborate, and bis trifluoro sulfonamide. So these structures you can see for this melting point is 79, and for BF4 this is 11 degrees centigrade, and for this one the melting point goes below room temperature, minus 15 degrees centigrade. So such ionic liquids have negligible volatility, high thermal stability, chemical stability, high ion conductivity. And say for this, this is the cation, this is anion. This combination actually gives rise to aprotic ionic liquids. There is no active proton here. So by quaternization and ion exchange, we can prepare aprotic ionic liquids. But this can also be say prepared by combination of Bronsted acid and base. In fact, if we neutralize Bronsted acid with a base, then we can have also ionic liquids, and due to the presence of active proton, we can call it protic ionic liquids. And recently, there are two other types of ionic liquids as well: inorganic ionic liquids, solvent ionic liquids. So here I have shown the example. So today, actually, I will not show all these. I have cited these examples only to show that how versatile the field can be. And this may be not only controllable, but highly specific and highly controllable. So for ionic liquids, I have shown that there is a wide variation in structure and kinds of ionic liquids. So aprotic, protic, and even other ionic liquids can be prepared by different methods of synthesis. Thermal behaviors may be controlled. Physicochemical properties like density, molar concentration, viscosity, and conductivity may be changed. And ionicity, that is the very important parameter for ionic liquids, which can be judged by Walden plot or pulse gradient spin echo NMR. So this can also be varied. So to give tunability in the ionic liquid structure and physicochemical properties. So actually for all these variations, so ionic liquids find application in lithium polymer battery, electrode deposition of metal, fuel cell, solar cell, soft actuator, organic synthesis, electrochromic, and in fact, why not? And I have listed here the properties to be utilized and chemistry to be pursued. But here, the application I am going to show here, you see that does not directly cover any of this. So that is a new dimension. Even we can prepare band gap semiconductor by using ionic liquids. So why? Why ionic liquid should be serve that purpose? Can it be used as a template? Yes, because this is a liquid, and this can serve as a soft template. And the ionic liquids have good dissolving ability, exhibit high thermal stability, so low vapor pressure, have highly organized liquid structure, and recyclable. So if we can efficiently exploit these properties, we may be able to use ionic liquids as a template for preparation of zinc oxide nanostructures. Actually, this has already been reported, including us. I will show some of our results now, and then we shall move to the double salt ionic liquids. So the use of ionic liquids may be effective, as I already mentioned, as a self-directing agent and templating material for the successful preparation of zinc oxide nanostructures. So here actually in all this work has already been published in RSC Advances. So we have used 3 different ionic liquids. All are hydrophilic ionic liquids. You can see 1-ethyl-3-methyl-imidazolium, methyl sulfate, here ethyl sulfate, and we have also changed the cation here to 1-butyl-3-methyl-imidazole, lium, keeping methyl sulfate the common. So for these are the structures. And if we see the models like this, we can see that we can use these ionic liquids for preparation of zinc oxide by using the common hydrothermal method. So in autoclave, you need know that at elevated temperature, in fact, at 121 degree centigrade was found to be sufficient. And after sterilization of 2 hours, so we could prepare synthesize zinc oxide nanoparticle, and after centrifugation and drying, we could finally have zinc oxide nanostructures. And say we first at a glance checked by dynamic light scattering by photon correlation spectroscopy, and we have seen that you can see the diameter here. This is dependent on, this is 0 means no ionic liquid, and we have changed the concentration. For this is 1 ionic liquid, this is another, this is another. So actually we have seen that the Z average diameter is dependent on structure and concentration of hydrophilic ionic liquids. So this is DLS. So actually this is hydrodynamic diameter. So to check the real diameter, we had to carry out some electron microscopic measurements, and naturally we carried out FESM studies without ionic liquid as well as ionic liquids of different kinds at different concentrations. And you can see that the structure varied from flower shaped, petal shaped, flake shaped. This is dependent on concentration, and also depending on the type of the ionic liquid, the size changed from cross, needle and flake. And here star-like, here you can see like flower, and this is a beautiful flower. So the morphology was very widely varied and controllable. So without ionic liquid and with ionic liquid, we have also checked the say selected area electron diffraction, as well as we have checked the TEM, HR-TEM studies, and the interplanar spacing between the adjacent to 0,002 lattice planes of zinc oxide nanoparticles is around 0.25 nanometer, to indicate that the zinc oxide exhibits a preferred growth orientation along the 0,001 crystal axis. So we can have crystalline behavior, and please listen carefully that the growth can be controlled at certain direction. This is actually very interesting. So we shall exploit these properties for use in the double salt ionic liquids. And for ionic liquids, we have determined the band gap energy by very common Kubelka-Munk method by using specular reflector spectroscopy. So we can see that the band gap has also been controllable by change in the structure of the ionic liquids as well as the concentration of the ionic liquids. And we tried, actually, Rajiv Gandhi, one Indian from who worked also on ionic liquid to control the morphology. He proposed some mechanism. We have extended that mechanism in our publication, and we could establish that by staking interaction, electrostatic interaction, and hydrogen bonding all collectively give some directional growth to the zinc oxide nanoparticles. So after nucleation, so depending on the structure of the ionic liquids and concentration of the ionic liquids, the morphology varies. And smaller alkyl group at the subsidiary chain of the imidazole cation in ionic liquid give the larger size of the nanoparticles and vice versa. So now the most important question, why do we choose a double salt ionic liquid then? So ionic liquid have certain control, so certain direction, the structure can be controlled in certain direction. So double salt ionic liquids, what are these? We know double salt, like say alum. Double salt ionic liquid consists of two pure ionic liquids with common cation or common anion. For example, here if C2-meme, the cation is the common, we can vary the anion, two different anions with widely varying properties. So if we combine these two, then we can have a mixture of ionic liquids, and interestingly, we can change the mole fraction of the ionic liquids. Say we can make 25-75 mixture, or 50-50, or 75-25. In many different combinations, we can prepare double salt ionic liquids and try to check the properties and their impact on the growth of the zinc oxide nanoparticles. So advantage of double salt ionic liquid over pure ionic liquid is that the enhancement of the self-assembled structure that can be controlled, and it can be more organized for the growth profile and expected synergistic effect. Two anions may collectively give some synergism in the properties, and they may overcome limitations of parent ionic liquid. We shall shortly see how these have really been achieved. So the synthesis is exactly similar. We have the precursor here, we have used zinc nitrate, and for ionic liquids, we have used double salt ionic liquids and the sodium hydroxide. These are all common, and hydrothermal reactor, Teflon container, and here temperature has been set to 120 degrees centigrade. And after drying the product at 60 degrees centigrade for 5 hours, we could have our product separated. And the reaction scheme is also exactly similar to that previously reported for the single ionic liquid. And when we compared the Fourier transform infrared spectral analysis, we have actually found all the profiles necessary to establish zinc oxide nanoparticles. And the characteristics, zinc oxide vibration band was observed in all cases. And double salt ionic liquid served as a better soft template for the synthesis of zinc oxide nanoparticles compared to pure ionic liquids. And when we checked the EDX, energy dispersive X-ray spectral analysis, we could confirm the presence of zinc and oxygen, and which confirmed the successful synthesis of zinc oxide nanoparticles. But the problem is we could also find the presence of slightly say ionic liquids or double salt ionic liquids with the zinc oxide nanoparticles. Some are adhered to the surface of the zinc oxide nanoparticles. So dynamic light scattering measurements were again used for the gross approximation of the say variation of the size, and we can see that this is zero ionic liquid. Here we can see that this is for ionic liquid. These are single ionic liquids. So like before, we could find a variation here. And for both ionic liquids, the intermediate concentration was optimum for the production of nanoparticles with smaller diameter and uniformity. That means if the width is smaller, we can expect a uniform structure. So uniformity was better obtained from imine acetate. However, for both ionic liquids, the highest concentration provided uniform size. So some controllability, some tunability was found for the individual ionic liquids. And when we checked, you can see here 0.3, 0.7, these are in mole fraction, 0.5, 0.5, this is equimolar, this is 0.7 and 0.3, and no ionic liquid. So here again, we can find some controllability. So double salt ionic liquids provided the smallest diameter of zinc oxide nanoparticles among all the reaction media. For unequal mole ratio, for example, 0.3, 0.7, and 0.7, 0.3, ratio of the anions, non-uniform size was obtained, and highest concentration of this anion caused the smallest diameter, while increasing concentration of acetate anion provided uniformity, thus proving their individual performances synergistically in double salt ionic liquid. So if we have the mixture, we can find something different. That means when two ions are present together, they give some advantageous feature in the system. So now let us move to the field emissions scanning electron microscopic image analysis. And here is the beauty actually. You can see that this is a single ionic liquid from 0 molar to 1.2 molar. We have checked the field emission images. You can see the here the structure is being changed for both the bis trifluorosulfan methane sulfonamide and acetate anion. First scheme, it shows nanoprism, hexagonal disc, and that gradually move to sharper hexagonal disc-like structure. And here from nanoprism, nano dyes, agglomerated dyes, and finally something like, you can see some rod-like structure here. And when we used, say, you can see double salt ionic liquids here, 0 molar, that means no. And here we have 0.3, 0.7, here 0.5, 0.5, and here 0.7, 0.3. And if we check the structure, you can notice the interesting variation again. So something like nanoprism, which converts to thicker hexagonal disc, and then interpenetrated disc. You can see here that one structure has been interpenetrated to the other structure. I will show the simplified scheme very soon. So then we check the XRD measurements also. And XRD measurements, you see that shows that these are highly crystalline. Woodite structure is here, and they have high phase purity. For here ionic liquid, single ionic liquid, no ionic liquid, and here say we can see that the double salt ionic liquids, so this crystallinity retained. And XRD measurements parameters are shown here along with the crystallite size, and the bis trifluoromethane sulfonamide anion caused protection of the lateral 100 facets, promoting growth in the 0001 direction. This is interesting. And for acetate anion, we see that the protection of 001 facet and promoted the growth along 1010 direction. That means two different anions say actually controlled the growth process in two different mechanisms. So different phases, different growth direction. That means if we combine these two to prepare double salt ionic liquids, so double salt ionic liquids provided the smallest crystallite size, again suggesting the advantageous effect of the multiple anions present. And say when we check the TEM images, so HR-TEM image of zinc oxide nanostructures, we have also found the selected area electron diffraction studies here. So these further support the data of XRD and field emission SAM, and SAD pattern shows the phase purity, D-spacing corresponding to the suggested growth direction. Dark spots represented the interpenetration of nanoparticles in double salt ionic liquids, and dominant role in shape controlling played by the acetate anion. So let us try to understand now the mechanism using simplified scheme. So reaction here, say zinc and these, and finally we prepared zinc oxide as I have shown before. So nucleation started, then clusters, and then the growth process. So if no ionic liquid, the shape is prism shaped. I have shown it already. If there is acetate anion, so you can see this growth is controlled. That means we can have only hexagonal disc. That means along this direction, ionic liquid have some interaction. And what does this see from upward to this? This growth is controlled. That means this growth is restricted, and therefore we can have just a disc of lower diameter or thickness. When we have, say, bistrifluoromethanesulfonimide anion, you can see that this direction is not controlled. This is becoming rod shaped. That means the control is now in this direction. So here this is control. So this cannot become, say, thicker, but this can become rod shaped. But if we have double salt ionic liquid, that means we have control from this direction as well as from the vertical direction. So control growth caused by the synergistic effect of anions. Two anions collectively, cumulatively affect the growth structure. So we have interpenetrated hexagonal disc as we have seen in the TAM and SAM images. So we can find the concentration effect here. So ionic liquid protection here, this direction for this anion along this direction. And we can see that if we increase the concentration, the disc thickness becomes, say, thinner and thinner. So it is thicker for without ionic liquid. And for this one, say this direction, this is becoming rod-like, longer and longer, because the control is now here along this direction, and along this direction diameter does not change. And double salt ionic liquid, since there is a control from both directions, we have a structure in between like this cluster, and ultimately they become interpenetrated discs. So now let us show the schematic presentation of the mechanism of formation here. So here, if individual cation and anion, I have shown that referring to the paper by Gandhi et al. So they have shown this structure, some pi-pi interaction, electrostatic and hydrogen bonding. There is a control here. And if there is double salt ionic liquid, actually C is there. So we have, say, control from two sides, two opposite sides. That means here, this is one anion, this is another anion. So these, so both control are being applied here. So we have interpenetrated structure. Finally, we will show the results of some preliminary results of photoluminescence. Here, actually, I have shown photoluminescence spectral analysis of synthesized zinc oxide structure. Excitation wavelength was 325 nanometer. And you can see that depending on the structure of the ionic liquids and double salt ionic liquids, we can see that strong red emission with negligible UV emission can be observed, and higher intensity peaks found for double salt ionic liquids supported the aggregation and interpenetrating behaviors of the nanoparticles, and strong defect emission peak could be caused by the intrinsic defect. And if we check the, say, photoluminescence spectral analysis of the zinc oxide nanoparticles, we can see that the conduction band and band gap, this showed some changes, because the schematic representation show the defect energy levels of zinc oxide responsible for red emission. Red emission and blue, this corresponds to non-radiative emission, and red shows the corresponding red emission. And since this level is being changed, so we can actually comment that the probability of the neutral oxygen vacancies would be the best option to cause the red emission, and hydrothermal route for the production of nanoparticles could be essential to introduce distinct defects. This defect could be significant for the advancement of optoelectronic devices. So now it is the time to conclude. So actually, zinc oxide nanoparticles could be successfully prepared from double salt ionic liquids as soft templates using hydrothermal route, as I have shown, and double salt ionic liquids perform better than parent ionic liquids. And these double salts provided the smallest particle size corresponding to the cooperative effects of the anions in the double salt ionic liquid media and distinct variation in morphology, as you could already notice, achieved. And strong red emission and negligible UV emission were observed from zinc oxide nanoparticles to demonstrate their potential for optoelectronic devices. So actually, this is a group picture of our recent tour we made from our material chemistry research laboratory in the Department of Chemistry, University of Dhaka. So it could have been better if I could join the conference in person that have discussion with you, but at least I tried to summarize my results in simplified way so that using the technology, I can at least have some interaction with you. Thank you for giving the opportunity to at least present by the Zoom platform. Thank you.
Thank you very much, Professor Sushan, for your wonderful talk covering different aspects of exploitation of ionic liquid in the synthesis of xenon nanoparticle. We are really running short of time. We can have a single question from audience. Please, Adhikar.
Hello, Assalamu alaikum, Professor Susan. Very nice to see you here. I expected that you will be here, but you could not come. Yeah, you gave very nice lecture. Thank you so much for the lecture. And I have a query. If this method of controlling the morphology of the nanocrystals could be extended to other nanoparticles, metallic nanoparticles, double oxides, and even if it could be extended to bimetallic nanoparticles. So can you please give some comment on it? So thank you so much and see you soon again.
Yes, sure. We shall see you maybe in India again very soon. Okay. So thank you for the very nice comment actually. So our first idea was to try with the simplest one, zinc oxide nanoparticle. And then actually I am almost in a position to present in next conference. We have extended the exactly same concept to other nanoparticles. So here say even dielectric substances, some ferrites and also other materials. And this control has been made wonderfully to other systems as well. So if you are interested, I will say that this will be easily applicable to any nanomaterials of your choice. So far, we have been successful to apply this concept to at least two other different kinds of nanomaterials. It will be applied, definitely applied. Thank you.
Our next presentation, our next speaker is Professor Ravin Manohar Jugare from Nagpur University. Professor Jugare is very well-known face here in Nagpur. So I briefly mention that he received his PhD degree from Nagpur University in 2004. He has published more than 84 research papers with age index 21 and height index 38. He has 15 book publications in his credit.
Hello.
To continue the introduction of Futuristic, he received many awards and fellowships. Some of them are honorary fellowship, award by Indian Society for Analytical Scientists for the year 2022. He was awarded with the Guruvan Success Award by Vidya Shiksha Yosharak Mandal Nagpur in 2005. And at present he is working as a chairman, Board of Studies in Chemistry, RTM Nagpur University. So with this introduction, I invite Professor Jugare to present his talk.
A very good afternoon to all of you. Thank you very much for the nice introduction, sir. So this is as the organizers have asked me to finish in 15 minutes, so I will be trying to finish off my lecture in 14 minutes. So let's start with my topic, tailoring chitosan biopolymer for water detoxification. It's actually when I prepared it. Have you connected it? This one? Yes. Okay. So yeah. So I remember one of my professor, K.N. Munshi, many of you must be knowing him. He used to say the most difficult crowd to deliver lecture before the pre-lunch crowd, because the crowd is thinking of something to eat, because now it's around 1:30, a proper lunch time. So that's why I have decided to go with only 15 minutes talk. It is not changing anything. It's not changing. Yeah, I'm a strong believer of the fact that success is a journey and not a destination. This presentation of 15 or 20 minutes is just a journey of last 10 years, what we have done in our research laboratory in Nagpur University Analytical Chemistry Research Laboratory. Next one. We have worked on a compound called as chitosan, which is derived from the crustacean shell wastes. This crustacean shell waste is converted into chitosan by two methods. One is the chemical method by treatment with HCl, then NaOH, and then deacetylation to give chitosan from chitin. And the second method is a biological method where the harsh acids and bases are avoided. And on the contrary, what we use are the protease and enzymes, leading to formation of chitin, which is further deacetylated to give chitosan. Next one. It is the second largest available biopolymer in nature after cellulose, and it has found a large number of applications in various fields like agriculture, food chemistry, then pharmaceutical industry, cosmetics, paper industry, medical devices, all of this. The area in which we are working is a water treatment. And when we go through a literature for last 10 years, you will find that the number of publications where chitosan used as adsorbent for water treatment application is continuously increasing day by day. And I haven't updated it to 2023, but it is up to 22 only. You will find that large number of publications are available in last 10 years. So it is the most current area of research. Next one. The important properties why chitosan we have selected is the important properties of the chitosan are, it is basically a biopolymer, a natural origin of compound, very high hydrophobicity, its biocompatibility, its biodegradability, and non-toxicity. It is used as a food supplement also. That is the non-toxicity of, it's a clear indicator of non-toxicity of chitosan. Apart from that, the chemistry point of view, it has got two important reactive groups, that is the amino group and OH group, which can be modified structurally. We will see that the specific modifications are possible, and it is possible to develop certain composites and regenerate and reuse the material again and again for water treatment applications. Next one. Next. So the water treatment technologies are, a large number of technologies are available. Among them, I will be focusing mainly on the adsorption phenomena. Next one. So when we talk about chitosan as a water treatment agent, the native chitosan or the pure chitosan then we use as an adsorbent, it can be used, and it has been reported in the literature for last more than 20 years that it can be used for capturing the various metal ions because of this OH and NH2 functionality which are having the lone pairs, and they can form coordinate bonds with various metal ions, and it is possible to capture many of the metal ions of environmental importance, including the cadmium and lead, nickel, copper, etc. And all of them can be captured by using the complexation phenomena by chitosan, NH2 and OH functionality. There are two models which are available in the literature or reported in the literature: the pendant model and the bridge model, where the metal ions get trapped into the chitosan matrix. Then, if the chitosan is already available as a material that can detoxify various metal ions, then what is the requirement for modifications of chitosan? So, if you see the adsorption capacity for most of the ions, the adsorption capacities are very low. Our aim is to improve the adsorption capacity of chitosan by improving it functionally and chemically and morphologically. Next one. Next one. Yes, what we do in our lab. So what we do is we carry out chemical and physical modifications of chitosan, followed by the characterization and then application to various adsorption studies, followed by the theoretical aspects, including the response surface methodology, the RSM modeling study. The chemical modifications which we carry out are simple, like cross-link, impregnation, grafting, then combination of all of them, then composite formation, and some gamma degradation also. Physical modifications can be molding the chitosan biopolymer into beads or microspheres, then nanofibers, then magnetic beads can also be modified, then hydrogel formation, aerogel formation. All these physical modifications are also possible. The first thing which we have reported on, it is available in the literature also, that cross-linking is the most easiest way of carrying out modifications in the chitosan matrix. It can be done by two ways. One, by using a multivalent ion, or second, by using a multifunctional organic compound. Multivalent ions, when we use, next one. So if we simply take chitosan and carry out a reaction with simple, multivalent acids, like say H2SO4 or phosphoric acid, you will find that the NH2 group gets converted into a protonated amine group, and then the anionic part of this, next one, the anionic part of this can act as a bridge between the two. So it is an ionic cross-linking between the two by using a multivalent ion or multivalent acid. Next one. There is a possibility of covalent cross-linking. The basic chemistry knowledge tells me that the NH2 group can be combined with the aldehyde group, and if I use an aldehyde like glutaraldehyde, or say any dialdehyde other than glutaraldehyde, it can act as a bridge between the NH2 groups of the two chitosan moieties, and we can carry out the cross-linking of chitosan by using such type of glutaraldehyde. But the problem of this is that, the NH2 functionality which was present over here is lost because of the cross-linking phenomena. Next one. Another way of carrying out the cross-linking is better than that. That is, the epichlorohydrin can be used as a cross-linking agent, which does not cross-link to the NH2 group, but cross-link to the OH groups, and as a result, this NH2 functionality is preserved. So there is another way of cross-linking chitosan. Next one. There is a possibility of we can use some say polycarboxylic acids. So we can have a combination of both covalent cross-linking as well as ionic cross-linking. Next one. What we did, we started our work with chitosan, and it was reported in literature long back in 2009 that native chitosan can be used as an adsorbent for chromium with an adsorption capacity of 22 milligrams per gram. What we did is we just carried out a simple cross-linking with sulfuric acid, and we found that the cross-linked chitosan, which was formed by sulfuric acid cross-linking, improved the chromium adsorption capacity to about 157 milligrams per gram. So from 22, we improved it to 157 milligrams per gram. Next one. Further, we carried out one more type of cross-linking by using a simple oxalic acid. Again, the adsorption capacity for chromium was improved to 348 milligrams per gram. Next slide. we have used, or we were probably the first to use the metallic cross-linkers like stannic chloride. SnCl4 was used as a cross-linking agent for removal of arsenic 3 from water, and the absorption capacity for arsenic was found to be 266 milligrams per gram, whereas the native chitosan or the pure chitosan is having only 1.83 milligrams per gram. Similarly, we have carried out the similar studies with fluoride. Now, chitosan has negligible absorption capacity towards fluoride, but we carried out this by using SnCl4. When we cross-linked with SnCl4, the fluoride absorption capacity was found to improve from negligible to 14.8 milligrams per gram. Second way of carrying out the modification is grafting. Now, because we are having the NH2 group and OH group, large number of graftings are possible on these functional groups. There is a possibility of synergistic effect of two, cross-linking at the same time grafting. So cross-linking as well as grafting, we have reported for various metals as well as non-metallic species. Like chromium, we have reported the chitosan is having only 22 milligrams per gram. Sulfate cross-linked chitosan is 157. But when we have sulfate cross-linked chitosan along with the impregnation with ionic liquid aliphat 56, the further improvement in the chromium absorption capacity was observed. Similar is the effect when we use some ionic liquids impregnated on this. Next one. There is another way of doing the things, the composite formation. Nowadays, we will find that there are a large number of composite formations are reported in the literature. So there can be, we have reported two types of composites: the organic inorganic composites and organic composites. This is a material where we have used the red mud, which is the best material obtained from the alumina industry. So red mud is another problem to the environment. So we have used the red mud and chitosan and prepared the microspheres of this for the removal of next one, various anions from water body. Next. Next. So, taking okay. Back. Back. You will find that it can remove fluoride, it can remove chromate, it can remove phosphate simultaneously, all of them. Another example is chitosan with zirconia microball. It is formed and the composite was found to have very good phosphate as well as chromium absorption capacity. Next one. Yes, this is zirconia chitosan beads were formed and it was used for removal of fluoride from water. It has very good absorption capacity, 52.6 is one of the very good reported literature for fluoride removal. Similarly, mesoporous chitosan, zirconia, ferrosulfuric oxide, again a magnetic type of material was used for fluoride removal. Next one. This is an organic composite, which is a composite of glucuronidine, tropic, chitosan, and alginate, both of them together for removal of next one. Various dyes like brilliant green, methyl orange, and various dyes at the same time, or simultaneous removal of the dye from water. Recently, what we have done is we have carried out modifications of chitosan in various ways. The PLK, which is a partially lateralized thondolite, it is coming from the ore of alumina, and it was clubbed with chitosan and forming the beads in two ways. One, chitosan PLK beads and chitosan PLK beads with cross-link with epichlorohydrin. And it was found that next one, they are having very good absorption tendency towards cyanide ions from water body. So 23.98 milligrams per gram and 55.27 milligrams per gram. All of these are reported and they have been published in various journals. There is another dual modification of chitosan with oxalic acid and biochar, and the composite was found to have increasing chromium absorption capacity with further improvements. Next one. This is another work where we have reported novel chitosan Zedano nanocomposite for the removal of three important dyes from water body. Recently, it is published in 2024. Next one. It has shown, the material has shown very good adsorption tendencies for three important dyes: the reactive blue, and reactive orange, and Congo red black. Next one. Next one. Okay, so this is another way of physical modification. We have reported the membrane is formed by cytosine with glutamic acid, and the membrane was used, next one, to absorb chromium as well as cyanide. You can see that the membrane is having a white color, and when it absorbs chromium 6, it becomes completely yellow in color. Next one. Yes, recently we have reported this cytosine barbituric acid. It's again a nitrogen functionality introduction into the cytosine matrix for the removal of chromium, as well as cyanide ions. Recently published in 2024. It is in the form of a hydrogel. Again, a physical modification. Next one. It's a magnetic hydrogel formed by a combination of cytosine, graphite, and polyvinyl alcohol. Right. For the removal of again a reactive orange dye. Recently, we have reported this cross-linked trim-phase derived cytosine for the removal of arsenic piles. Next one. I think I am in time, and my complete work credit goes to my students, group of 14 students working continuously in the lab. Today also 5 students are continuously working in my laboratory, and all the credit goes to them. Next one. We have 2 important international collaborations with South Korea, Dr. Salanan Pandey. Recently, he has joined Shulini University of Himachal Pradesh, and one Dr. Asif Lila from Morocco. Thank you very much.
Thank you, Professor Jugadan, for your nice presentation on the interesting polymer and context to water treatment. So I find there are many interesting points in your talk, and may have some questions. So due to time constraint, we are postponing this question and interaction.
We can discuss it in the
lunch
next
session.
session.
Thank you very much for your cooperation. Thank you.
Thank you, sir. I would like to felicitate Professor Jugadan, sir. So I request Dr. Das, sir, to felicitate Professor Jugadan.
Well, next we move to our next talk. Speaker is Dr. Amit Bapana from Niri Nagpur. He is Senior Principal Scientist, Waste and Chemical Toxicity Assessment, CSIR, Niri. Dr. Bapana did his PhD from Nagpur University, and his degree was awarded in 2011. Some of the notable achievements of Dr. Bapana is he received National Merit Scholarship, Junior Research Fellowship, CSIR. He qualified Sama Prasad Mukherjee Fellowship, CSIR. He was awarded INSA Visiting Scientist Fellowship in 2014 and 15. He has contributed to over 40 R&D and consultancy projects. He has more than 55 SCI journals in credit. He has contributed 3 book chapters in reputed publishing house, and he attended and participated in more than 26 conferences. So with this introduction, I invite Dr. Bapana to present his talk.
Thank you for that question. So I am Manish Bhapna from Navy Nagpur. I will find qualitative online infrastructure. So I'm going to talk about production of bioplastic from lipid-rich wastewater. So in the form of, you can say, a biopolymer or a biomaterial form of bioplastic. So I think importance of plastic replacement, any sustainable replacement for plastic need not be stated. Plastic is a very widespread pollutant, now leading to newer kind of pollutants like microplastics, nanoplastics, like fragmentation. So work on bioplastics has been going on for quite some time. But here, what additional novelty we have added is we have targeted lipid-rich wastewater and try to couple it with bioplastic production. And what is the reason for that? We'll see in the following slide. Okay, so challenge of wastewater. So anyway, challenge wastewater treatment is also very necessary because wastewater for domestic or industrial leads to again pollution of soil, water bodies, there. And that particularly lipid-based poses a particular challenge because lipids are insoluble in water. They form a surface layer. They don't tend to mix them and make the treatment process more difficult. So the most commonly used treatment method for lipid wastewater, like food wastewater, is dissolved air filtration (DAF). But problem with DAF is that it doesn't completely really remove the lipids, and after DAF treatment, also a lot of lipid emulsified lipid is left in wastewater, which is very difficult to do. And of course, after DAF, whatever lipid can be removed, that is taken to by industry to some other processes like biogas production. Also, that is utilized well. So that is good basically recycled. But what about the emulsified lipid which is present and which constitutes about 10 grams per liter or that high content? So with this background, we started with our work to find out how this can be converted to other values. So in this, yes. So of course, there are different kinds of bioplastics. The kind of bioplastic that here we have targeted are polyhydroxyalkanoids. So they are biopolymers, which are nothing but polymers of, as the name suggests, beta hydroxyalkanoic acid. The simplest of them is polyhydroxybutyric acid, which is polymer of beta hydroxybutyric acid. And polyhydroxybutyric acid is a short chain monomer. So it tends to be more rigid kind of replacement for polypropylene. And as the chain length grows longer, they become more flexible. So maybe the higher alkanoids can be used for replacement of polyethylene and all. So they are non-toxic, completely biodegradable as compared to compostable plastics which are available in market. So yes, a lot of work has been done and a lot of potential is there, but it has to be economically feasible to hit the market because comparatively the plastic cost is very cheap. So how this polyhydroxyalkanoids or PHs are used? So PHs are nothing but reserve materials of microorganisms. Whenever and if you see their composition, they are composed only of carbon, hydrogen, and oxygen, no nitrogen. So whenever carbon to nitrogen ratio is very high, carbon source is available in abundance, or organisms like bacteria are in stress conditions. They cannot really grow because of say adverse pH, adverse temperature, adverse nutrient medium. So they tend to accumulate this carbon in the form of reserve materials, in the form of granules. These are called as PHA granules. PHP granules being the most common. Then there are phosphate chromatic granules and other kind of reserve materials, but this is the most common reserve material for carbon. Some of them also accumulate starch and cellulose, but they are not that useful for bioplastic application. So in literature, again, as I said, lot of studies have been done and different productivity has been obtained. So we'll see in light of this what our results are. Okay, so with this, our objective was to first of all to identify high lipid organisms, because if you want to use a lipid base for PHA production, the organism bacteria should be able to hydrolyze lipid well, and at the same time produce PHA, and then we characterize the lipase activities, and then we applied it to synthetic wastewater as well as real world wastewater from food industry. Of course, post DFA treatment, DF treatment, and analyze the PHA production. In this, why, as we discussed earlier, that why we use lipid was that if you see, actually, I should have had slide for that. I'm sorry, I did not have it. If you see the lipid degradation pathway, it's a triazide glycerol. So it is first hydrolyzed to glycerol and fatty acids, and then these fatty acids are catabolized finally to acetyl coenzyme. That is the final monomer. And if you see the PHA production pathway, it starts from acetyl coenzyme. So the end product, or you can say the intermediate of lipid catabolism, is substrate for PHA production for anabolic reaction. So that is the commonality, and that is why we thought that this might be the best approach for PHA production, and of course at the same time treat the wastewater. So first of all, we went ahead with our lipid lipase organism. We analyzed lot of organisms, and out of that we found out 100 of them, about 100 of them produce lipase, good lipase activity on plate testing. Then we carried out proper PHP testing and secondary screening, and out of them then we selected 20 different bacteria which produce lipase. Now, reason here is that the plate acid tributylene is which is a short chain fatty acid, which contains short chain fatty acid. So even non-lipase esterase, there can be confusion. Esterase enzyme can also hydrolyze, but for secondary screening we use para-nitrogen palmitate. Palmitate is a long chain fatty acid. So the organism which are able to hydrolyze them, they will be able to hydrolyze even the waste oil, containing long chain fatty acid. So out of these 20, then we screen them further for lipase activity PHA production, and we found that 3 of them showed good PHA production. Out of these, I-87 and isolate showed very good PHA production and all that. So that was selected for further. So this is a slide. Then we identified. So it was identified as bacillus halotolerant species, so non-pathogenic commensal organism. And its halotolerance, we check for its halotolerance. It should go well up to 10% NaCl also, but it's not really halophile. It is halotolerant species. So it grew best at normal physiological, normal NaCl concentration. So it was fit for our purpose, and it was identified by RNA sequencing. Its PHA production we analyzed by Sudan blackfish staining in plate as well as in under microscope. It showed PHA granules. So yes, then first of all we studied lipase production, because that lipase production had to be high. We did lipase testing, but then we had to find out what lipase profile it shows. So it shows time profile of lipase activity, how it increases with time. Then the lipase activity, so it was very good showing activity right from 4 degrees centigrade to 3 degrees centigrade, almost constant. So very wide range of temperature. So it can work in any season, winter, summer, all. And pH also is the profile pH 7 to pH 9, very good active. So it had a correct profile that we needed for our treatment and PHA production. And then we also tested for our curiosity its other properties like solvents and all. If you want to use this lipase for some other purpose, because lipases are used for a lot of synthetic reactions in solvents. So it shows good solvent tolerance also in many of the cases. So then further we went ahead with our study on PHA production. Yes, one more slide on lipase. Then we tried to study what kind of lipase enzyme it has. So we did not, of course, purify it. but we did a native phase, native polyacrylamide gel electrophoresis, where the enzyme is not denatured and you can visualize it by activity staining. The activity staining was done on chromogenic agar, where we simply add substrate along with knowledge because of hydrolysis, fatty acids will be released, pH will decrease, and a color change will be observed. So now red showed yellow color, clearly showing, and we compared it with our protein ladder, and it shows around 45 kDa and 45 kilodalton, and in literature it's lipases are normally dimer, so maybe it has some monomeric molecular weight of 22.5 or between 20 to 25. So next, so of course we are working on it further to clone it and utilize it for other and one more result from is that the single binding, it contains a single extracellular enzyme. There are no two enzymes. We are working on purifying cloning it so that it can be used for other purposes because it shows very good temperature and heat. Right? Now in coming to wastewater treatment, which was the meaning. Yes, so we had a synthetic wastewater because of course with literature if we have to compare our wastewater won't compare. So synthetic wastewater was used and a real world wastewater was collected from ATP effluent treatment plant of a food industry where the oil concentration was very high and next thing. So after treatment the results were as follows. So if you see the initial concentration of wastewater liquid concentration in terms of oil and grease was around 14.7 gram per liter. This is after dissolved air fluoridation. So a lot of liquid is really going into the drain and causing secondary problems. So we saw that in PHC production medium, that is synthetic medium, containing 1 gram per liter of oil. The PHC production medium contains glucose and peptone as other carbon sources apart from oil. So we got the best in the PHC production medium, synthetic medium, which is expected because it is under control condition, 4.8 grams per liter. And in nutrient growth, other we also, and one interesting saw that when we do the experiment in the absence of oil, the third column you can see, the fourth column, in wastewater, if we don't add our culture, then we did not get any PHA production. That is the native microflora which were being used in that treatment plant. They did not use, they were not able to produce any PHA. There was no PHA production, but once we add our strain to wastewater, we got up to 2.3 gram per liter and 2.9 gram per liter of PHA in wastewater. And in PHA production medium and nutrient growth, it was even higher up to 4.8 gram per liter and 3.6 gram per liter. Then we extracted this by solvent extraction and purified it and characterized it further in next slide. Okay, so this was characterized first of all by GCMS because we wanted to know is it polyhydroxy butyrate or what monomers are there present in it. So by GCMS we got several things indicating that it consists of many different fatty acids which are shown in next slide. So if you see the composition, it varies from C9 to C13, then C18 and C14. So you can see C9 to C18 different chain lengths inside. So it was a mixture of different kinds of beta hydroxy. So it's you can say a medium chain length polyhydroxy alkanoic acid, not corresponding to really butyric acid, which is more common. So this can be a good substitute for you can say a flexible kind of plastic like polyethylene. So in conclusion, we saw that we got a very good strain which had good lipase activity as well as good lipase stability, and it produced very high pH, 4.8 gram per liter in pH, and in wastewater up to 2.9 gram, which is very high because in literature the range in wastewater. In wastewater, the values range from say 0.5 to onward. So yield was good in that sense, and of course we can further optimize it for this. So PHA was not detected in untreated wastewater where we did not add our inoculum under same conditions. So presence of this culture is very important. It really played the role. Now our future scope next plan is that we want to clone this enzyme, and already we have cloned it actually. But it is entering inclusion body, so we are working on it. Maybe because it's an extracellular enzyme, that might be there. And also we are trying to scale up this PHA production with industry to see if they give us a small space and we can demonstrate there what can we do with wastewater and how to extract it. So it will be value addition. So So I think thank you so much for your patient listening. Thank you so much. And thank you also to Bangladesh to give me an opportunity to speak here. Thank you.
Thank you, Dr. Vapana, for your nice presentation. And I believe those who are working in this area beginning to get from the top. And there are some interesting points that scope of interaction, but that can be done in lunches and time. Thank you. So,
I would like to felicitate Dr. Bhavna sir. So I request Dr. Das sir to offer to give the certificate to Dr. Bhavna sir.
so thank you everyone for being present here. So in this session, we have 5 interesting lectures from international speakers. I thank you all the speakers and the audience as well for their kind presence and question period. So thank you all.
Okay. Now here the session. In this session, all speakers are given their expert talk, invited talks. Now there is time for lunch. So we take first lunch and then we will start remaining oral presentations. Okay. So I take attendance. So there will be remaining 3 presentators in earlier list. So they will give first their presentation, and after that, the remaining 10 presentations are here. Okay. I would like to felicitate Dr. Das sir. I request Dr. Gurnule sir to felicitate Dr. Das sir.
You are going for the lunch, okay? And immediately after the lunch, come here in the hall, okay? We start remaining oral presentations, okay? Oral presentations are here also and also in another hall, okay? Thank you, Sonia madam and Professor Susan sir. We are ending this meeting now. I am very, very thankful on behalf of Kamlani Mahavidyalaya for joining and giving wonderful presentations. Thank you, sir. Thank you, madam.